Hey folks, how's it going? Mr. Mitchell here. In this video we're going to go over section 1, i.e. the multiple choice questions from the 2019 SQA National 5 Physics exam paper. Now there are 25 questions in this section and I recommend that you try them yourself before looking at these solutions. So let's get into it. Question 1 says, which of the following are both vectors? Well, remember a vector quantity is one that has both a magnitude, i.e. a size, and a direction, and so we want to see which ones are both vectors. Well, if we look at A first of all, weight and acceleration, remember weight is a type of force and force is a vector, so weight must also be a vector, and since acceleration is also a vector, then that means that A is going to be our answer here. We can also see scalars in the other ones, so for B we've got kinetic energy as a scalar, mass is a scalar for C, speed is a scalar for D and for E. Question 2 says a car is travelling at 6 meters per second along a straight level road. The car then accelerates uniformly at 2 meters per second squared for 4 seconds. The final speed of the car is. Well, notice how we're given an acceleration, an initial speed and a time, and we're asked to calculate the final speed. So this suggests we need to use the equation for acceleration, which is A equals V minus U over T. So let's sub in the numbers. So we have 2.0 for the acceleration equals V minus the 6.0 for the initial speed divided by 4.0 for the time. And let's cross multiply to get 2 times 4, which is 8, is equal to V minus 6. And then we can add 6 to both sides to get V equals 8 plus 6, which gives a final answer of 14 meters per second, which gives us the answer B. Question 3 says the graph shows how the speed V of a car varies with time t. During which part of the journey does the car have the greatest acceleration? So you can see we've got V in meters per second and then time in seconds. So you should already know that acceleration is given by the gradient of the line on a velocity time graph. And in this case, because we want the greatest acceleration, we want to look for the steepest part on the graph. So the greatest acceleration is equal to the steepest gradient on the velocity time graph, or the steepest line, which is going to be S to T here. So that is going to be the answer E. Question 4 says a ball is kicked horizontally off a higher riverbank as shown. So we've got the ball projected at 8 meters per second horizontally and it's landing at point X on the lower riverbank, which is a distance of 3 meters plus D to get to X. It then says the ball lands on the lower riverbank at X 2 seconds after the ball is kicked. The river is 3.0 meters wide. The effect of air resistance on the ball is negligible. The distance D between the edge of the lower riverbank and X is. So we want to find this distance D here. So the strategy we're going to use is to first find the horizontal distance travelled, i.e. the range, which is this full distance here, and then subtract the 3 meters for it to get what D is. And because we've got the horizontal speed and we've got the time of flight, which remember the time of flight is the same for both horizontal motion and vertical motion, that means we can use the equation for horizontal motion here, which is speed distance time. So we have D equals Vt, where we can plug in the numbers of 8 meters per second times the 2 seconds for the time of flight, which is 16 meters. However, remember that is the total distance from here to here, the full range, and we want just the distance D, so we can say that distance D is equal to 16 minus the 3 meters, which gives us 13 meters, which is the answer C. Question 5 says that the table gives the distance from Earth, the approximate surface temperature and the age of 5 stars. A student makes the following statements based on this information. So this is purely a skills-based question because all the information we need is in the table and it's not really stuff that you would have covered in the National 5 course. So statement 1 says as the distance from Earth increases, the age of a star decreases. Statement 2, as the age of a star increases, the approximate surface temperature of the star increases. And statement 3, there is no apparent relationship between the distance from Earth and the approximate surface temperature of a star. Which of these statements is or are correct? Well, we're going to look at each statement in turn and decide which ones are true or false and look at the table to decide. So for statement 1, as the distance from Earth increases, the age of a star decreases. So if we look back at the table here, we can see that as the distance from the Earth increases, the age of the star does decrease, but then it increases again. So we can't say that that is true for the first statement. So the first statement must be false. Statement 2, as the age of a star increases, the approximate surface temperature of the star increases. So let's look back at the table. So as the age of the star increases, the approximate surface temperature increases. So let's look and see if that is true. Well, if we look at the age increasing up here first of all, then we can see that as age of the star increases, that the approximate surface temperature does increase. However, since 8 times 10 to the 6 would fit above this one after the 7.9 times 10 to the 6, then that suggests that this 11,000 Kelvin should fit in between these two numbers here, 3,600 and 6,000, but it doesn't because it's obviously much bigger than even the 9,900 here. So we can see that that pattern does not hold. So we don't have that as the age increases, the approximate surface temperature increases. So that is also going to be false. And then for statement 3, there's no apparent relationship between the distance from Earth and the approximate surface temperature of a star. Well, looking back at the table, we can see that as the distance from the Earth increases, the approximate surface temperature does decrease until we get to this point where it just randomly increases again and then decreases again. So we can say that there is no clear relationship here. So that statement must be true. So we can give that one a tick. So we can say that the only correct one is 3 only. So that gives us the answer C here. Question 6 says a geostationary satellite orbits the Earth. Which row in the table shows the altitude above the surface of the Earth and orbital period of the geostationary satellite? Well, there's two key things you need to remember for a geostationary satellite, and those are that it has an orbital period of 24 hours, i.e. 1 day, and it orbits the Earth at an altitude of 36,000 kilometers. And those two values are given here for answer B. Question 7 says the weight of a robot on Earth is 240 newtons. The weight of the robot on Mars is. So the strategy here is that we want to first find the mass on the Earth and then the weight on Mars, since the mass will be the same on Mars as it is on Earth, because remember, mass stays the same no matter what planet you're on. So let's use the equation W equals mg and rearrange for the mass to get m equals W over g, and let's plug in the weight on Earth, 240 newtons, and divide that by the gravitational field strength on Earth, g, which is 9.8 newtons per kilogram from the datasheet, and let's put that into your calculator to get an answer of 24.5 kilograms. And now we want to find the weight on Mars using the same equation, W equals mg, and let's substitute in the mass that we found, because that's going to be the mass on Mars as well, 24.5 times 3.7, where 3.7 newtons per kilogram is the gravitational field strength on Mars. Again, you can find that on your datasheet. And let's put that into our calculator to find the answer of 90.7 newtons. Let's also round it up to get approximately 91 newtons, and you'll see that as an answer here for answer C. Question 8 says a hairdryer is connected to a 230 volt supply. The current in the hairdryer is 2.0 amps. The electrical charge that passes through the hairdryer in 5 minutes is. Well, notice how we're asked to calculate charge. We're given a current and a time, and we can therefore use the equation relating charge, current and time, which is Q equals IT. So I'm going to use my current of 2 amps, but notice how time is given in 5 minutes. So I'm going to convert minutes into seconds, because remember, time is measured in seconds. So let's plug in the numbers to get 2.0 for the current, times 5 minutes times 60 to get it into seconds. So that's the same as 300 seconds. So 2 times 300 is the same as 600 coulombs. So our answer here is C. Question 9 says the graph shows how the resistance R of a thermistor varies with temperature T. The thermistor is connected in a circuit. At a temperature of 50 degrees, the current in the thermistor is 0.004 amps. So you can see the resistance is given in kilo ohms and temperature in degrees Celsius, and we have this sort of exponentially decaying curve. It then says at this temperature the voltage across the thermistor is. Well, looking back at the graph, if we want to get the voltage, we know the current at this certain temperature is this value here, and we can also find the resistance at this temperature from the graph. So let's look at 50 degrees Celsius and go up to the curve and then along, and we have a value of 2.0 kilo ohms, or 2000 ohms, or 2.0 times 10 to the 3 ohms. So let's plug that into our equation for Ohm's law, which is V equals IR. So we have V equals IR, which is equal to 0.004 times 2.0 times 10 to the 3, and putting that into your calculator should give you an answer of 8 volts, which is option D. Question 10 says a student sets up the circuit shown. In which circuit will both LEDs be lit? So we've got these circuits in A, B, C, D and E, and you need to remember that current flows from the negative terminal of the battery to the positive terminal of the battery. And you should also be aware that for an LED to work, remember it's a diode, so it's only going to let current flow through it in one direction. And we actually need the current to flow through the thick line part of the LED first. So for example, if we look at this one here, the current needs to hit this line bit first, so it needs to be travelling from right to left in this direction. So we can say that both LEDs must be oriented such that the current flows through the thick straight line part first. So that straight line part is what I mean on the LED. So for A, first of all, if we think about current going from negative to positive, it's going to flow down here, along here and through here, so that's fine. However, along here, it's going to hit this part of the LED first, so it's actually going to be stopped. So A is not going to be the correct answer here. For B, we've got the current leaving here and going again through here, so current's going to be stopped. For C, current's going to pass through here, which looks good, and then it's going to pass through here and along, but it's going to then be stopped by this LED because it's turned the wrong way round. For D, we've got the current leaving here, down here, and again current's going to be stopped. So the answer must be E here, but let's just check that it's going to make sense. So the current leaves here and passes through the straight line part first, so that looks good. It's then going to pass through the resistor and through this straight line part of the LED and back to the battery. So that looks good to me, so our answer is E. Next we have question 11, and it says a circuit is set up as shown. So we've got this control circuit, also known as a switching circuit or transistor switching circuit, and we've got this 6-volt battery with an LDR and a variable resistor, a transistor and a bulb or lamp. It then says the room temperature is 20 degrees Celsius and the lamp is initially off. And it then says the lamp will light when the light level is decreased below a certain value, the light level is increased above a certain value, the resistance of R is increased above a certain value, the battery voltage is reduced to 5 volts, or the temperature is increased above a certain value. Well, what we need to do here is think about light, because this is a light dependent resistor, an LDR, so it's going to change its resistance based on the light conditions. And notice that this is the lower component here, so whatever happens to the voltage across here is going to happen to the voltage across the transistor. So we're going to work backwards and start at the lamp. In order for the lamp to light, we need the voltage across the transistor to be high enough for the transistor to be switched on. So if we want the voltage to be high or increasing across this transistor, then that means that the voltage across the LDR must also be increasing. And for the voltage to be increasing or to be high, then we need the resistance of the LDR to be doing the same. It needs to be high as well, because remember, voltage and resistance do the same because they're proportional from Ohm's law. So if this has a high voltage across it and therefore a high resistance, then we need the light level to be decreasing in order to give a higher resistance. So that corresponds to this one here, which is option A, and that is going to be our correct answer. Notice the other ones, so this switching circuit is to do with light conditions, not temperature, so we can eliminate that. We've never seen anything to do with battery voltage changing, and the resistance of the variable resistor, we're not really interested in that one because it's the upper component and we wanted the lower component resistance. So A is the correct answer here. Question 12 says a circuit is set up as shown. So we've got a supply voltage, resistor R1, and then 2 resistors in parallel here, and they've each got their own voltmeters across them. It then says a student makes the following statements about the readings on the voltmeters. So we've got statement 1, V1 equals V2, statement 2, V2 equals V3, and statement 3, Vs equals V1 plus V2. It then says which of these statements must always be true. So let's look at statement 1 and use the circuit diagram to help us. So for statement 1, V1 must always be equal to V2. Well, that's not necessarily going to be the case, because that sort of just depends on the resistance values of the resistors and on what the share of voltage each of these things takes from the supply voltage. So we can't say that that is always going to be true. So we're going to put a cross next to that one. The second statement, V2 equals V3, well, if we look at the circuit diagram, we want to work out if V2 is always going to be equal to V3. And for this, we need an important circuit rule for voltage in a parallel circuit. So remember, the voltage across each branch in a parallel circuit is the same. So we can say the voltage across here is always going to be the same as the voltage across here. So that means that V2 and V3 must always be equal. So we can give this one a tick. And for the last statement, Vs equals V1 plus V2, looking back at the diagram, we can think about this circuit as being a potential divider circuit, where we've got the supply voltage, we've then got this component, and we could also think about this component as being an equivalent resistance, i.e. just a single resistor, where we've found, say, the combination resistance there. And remember, we've just said that V2 and V3 will always take the same value because these two components are in parallel. So for this one, we need a different circuit rule, which is for voltage in a series circuit, which says that the voltage across the components in a series circuit must add up to give the same as the supply voltage. So that's saying that V1 plus V2 must equals Vs. Or we could also say V1 plus V3 also equals Vs. So that means our last statement is also true. So we'll give that one a tick. So that means 2 and 3 only are correct, which gives us the answer D. Question 13 says a solid substance is placed in an insulated container and heated. The graph shows how the temperature T of the substance varies with time T. So we've got temperature on the y-axis against time on the x-axis. It then says to calculate the specific latent heat of fusion of the substance, a student would use the time from section. And to do this, we need to think about what fusion actually is. Remember, fusion is just a fancy word for melting. So because we're starting off at P with a solid substance, then as heat is applied to it and it gains temperature, at point Q it's going to start melting, and then it's going to finish melting at point R, at which point that solid substance is going to be completely turned into a liquid. So we can say that that melting process is happening between Q and R, which is the fusion. So to calculate the specific latent heat of fusion, they would use the time from Q to R, and that gives the answer B. Question 14 says the pressure P due to a liquid at a depth h is given by the relationship P equals rho gh, where rho is the density of the liquid and g is the gravitational field strength. Notice how you probably haven't seen this equation before, and that's because this is a skills question. It then says a liquid has a density of 990 kilograms per meter cubed. When the pressure due to the liquid is 1470 pascals, the depth in the liquid is. So we're trying to find the depth h, and we can therefore start with our equation and just plug in the numbers. So we have P equals rho gh. Let's sub in the numbers to get 1470 for the pressure is equal to 990 for the density times 9.8, which is the gravitational field strength on Earth, assuming that all this is happening on Earth, times h, which is the depth that we're trying to find. I would then do this part in your calculator and divide 1470 by that answer to get h is 0.15 meters, and that gives the answer B. Question 15 says a car is parked in the sun for some time. During this time, the air pressure inside the tyres increases. The reason for this increase in pressure is the volume occupied by the air particles in the tyres has increased, the force produced by the air particles in the tyres acts over a smaller area, the average spacing between the air particles in the tyres has increased, the increased temperature has made the air particles in the tyres expand, or lastly, the air particles in the tyres are moving with greater kinetic energy. Well, firstly, you should be thinking that this is to do with pressure and temperature because we're talking about the sun, and the sun produces heat and light. So the air tyre parked in the sun is going to increase in pressure because it's going to increase in temperature. So this question is getting at the idea of Gay-Lussac's law, or otherwise known as the pressure-temperature law. And remember, Gay-Lussac's law says that for a fixed mass of gas at constant volume, pressure is directly proportional to temperature in Kelvin. So if pressure increases, that's been due to an increase in temperature. And your eyes might straight away go to this statement here because it mentions increase in temperature. However, if we read this further, it says the increased temperature has made the air particles in the tyres expand. That is wrong physics because remember, the particles themselves in a gas don't actually change size, it's the space between them that do. So if we think about the kinetic model of gases for Gay-Lussac's law, we looked at this in the theory video for Gay-Lussac's law, so feel free to go and check that out if you're not quite sure how to explain this law in terms of the kinetic model. But you might remember that as temperature increases, we can say that the particles in the gas will gain kinetic energy and therefore speed, and therefore hit off the walls of the container more often, and therefore exert more force per unit area, and therefore increase the pressure. And if we look at all of these, we can see that as temperature increases, the air particles in the tyres are moving with greater kinetic energy. That was one of the steps that we just said in the kinetic model. So that is going to be our correct answer here, E. And that's because none of the others are actually steps in the kinetic model. Question 16 says the temperature of a sample of gas in a container is 20 degrees Celsius. The volume of the gas is 0.3 meters cubed. The container is free to expand in order to maintain a constant pressure. The temperature of the gas is increased to 50 degrees Celsius. The volume now occupied by the gas is. Well, notice we've got a constant pressure and we've got volume and temperature changing. So this is referring to Charles's law, otherwise known as the volume temperature law. And we're also trying to find a final volume. So let's say we're trying to find V2 and we're going to write down the equation for Charles's law. And remember, this equation only holds when the temperatures are measured in Kelvin. So we need to convert both of these numbers into Kelvin by adding 273. So let's do that and plug in the numbers. So we have 0.3, the initial volume, divided by 20 plus 273. So that's getting the initial temperature into Kelvin. And that's equal to V2 over 50, the final temperature, plus 273, which is getting that into Kelvin as well. Then we can cross multiply here to get 20 plus 273 times the V2 is equal to 0.3 times this 50 plus 273. Simplifying that gives us 293 V2 equals 96.9. Then we can divide both sides by 293 to get V2 equals 0.33 meters cubed, which is the answer D. Question 17 says the following diagram gives information about a wave. So we've got from this point here all the way to this point here is 24 meters, and we've got the full vertical height is given as 6 meters. It then says which row in the table shows the amplitude and wavelength of the wave. Well, remember amplitude is defined as half the vertical height of the wave, which is the same as saying the height from the crest to the axis or the axis to the trough. The amplitude is simply going to be the 6 meters divided by 2, which is 3 meters. So we're looking at A or B as an option here, and then I want to count how many waves I have in this 24 meters. So starting off here, going all the way up, all the way down and back to the start, I have 1 wave, 2 waves, and 3 waves there. So I've got 3 waves in 24 meters. So for 1 wavelength, the distance of 1 wave, that's going to be 24 divided by 3, which gives me 8 meters. So I've got 3 and 8, which is the answer B here. Question 18 says a student is studying waves with a period of 80 milliseconds and a wavelength of 4 meters. The frequency of these waves is? Well, remember there's an equation relating period and frequency, which is T equals 1 over F. So the wavelength is actually being given here as a distractor to try and put you off and make you think you need that value, but you don't. So we're just going to ignore it here. So let's rearrange this to get F by swapping both the F and T to get F equals 1 over T. And you'll notice the period is given in 80 milliseconds, so we need to get rid of that prefix milli and convert it into seconds, because remember period is measured in seconds. So we have F equals 1 over T, which if we sub in our converted number is 1 over 80.0 times 10 to the minus 3. And if you put that into your calculator, you should get an answer of 12.5 Hertz. And that is the option C. Question 19 says, which of the following diagrams shows the diffraction of water waves as they pass between two walls? Well, you need to kind of be aware of two things here for a diffraction diagram, which is that for a diffraction diagram, you should remember that the spacing between the wavefronts or the waves, or the crests of the waves in this case, should be the same at all points. So the spacing between them should be the same. So in this one, we've got the same spacing, so that looks good. For B, we've got the same spacing as well. For C, we don't have the same spacing because the waves bunch up when they pass through the gap. For D, we've got the same spacing, and for E, we don't have the same spacing because the spacing gets bigger between the wavefronts there. So straight away we can eliminate C and E here. The second thing we should be aware of for diffraction diagrams is that when waves pass through a gap, they're going to bend at the edges. So we sort of have the straight part of the wave continuing, but then we're going to have bending around the edges. So we can eliminate option A there because they're not bending at the edges. For B, you can see that they're actually bending the whole way across the wave, which isn't what happens. You should have a straight part with the edges bending. So if we look at option D here, that is the only one left, which looks good because you've got the same distance between the wavefronts or the crests of the waves there, and you've got the straight waves continuing with the curved parts at the ends. So D is the correct answer here. Question 20 says a ray of red light passes through a glass block as shown. So we've got air here, glass block here, and the normal here. We've then got a ray of red light coming in and bending away from the normal. It says which row in the table shows the angle of incidence and the corresponding angle of refraction at point X. So remember the angle of incidence is measured between the incident ray and the normal. So that's the angle in here. And notice how this angle makes up 90 degrees. So in order to find this angle in here, we need to take this one away from 90. So we do I equals 90 minus 55 to get 35 degrees for this angle in here. We then need to do a similar thing for the angle of refraction, because remember angle of refraction is the angle measured between the refracted ray and the normal. So that's going to be this angle of 90 minus the 30 to get this angle in here. So R equals 90 minus 30, which is 60 degrees. And that means our answer is A. Moving on to question 21, it says which row in the table shows the path taken by alpha particles and gamma radiation as they pass through a uniform electric field between two metal plates. We've got path taken by alpha particles in the left column, and then we've got path taken by gamma radiation in the right hand side column. So we've got positive plates on the top and negative plates on the bottom, and we need to think about the charge first of all on these two particles. So remember an alpha particle is a helium nucleus, but we also define it as being 2 protons and 2 neutrons. So because neutrons have no charge and protons have a positive charge, then we can say that alpha particles must also have a positive charge. So that means that the positively charged alpha particle should curve downwards towards the negatively charged plate. And that's because positive and negative charges attract each other. So we can say that B does that and E does that, but all the rest we can eliminate. So it's going to be either B or E as our answer. And then for gamma radiation, remember a gamma ray is a high frequency, high energy electromagnetic wave, but because it's not a particle, that means it doesn't have any charge. So that means it's not going to be affected by an electric field between two charged parallel plates. So the gamma ray will actually pass straight through the electric field, just like in B here. So our answer is B. Question 22 says for a particular radioactive source, 1,800 atoms decay in a time of 3 minutes. The activity of the source is. Notice how we're given the number of decays and a time, so I'm going to use my equation for activity, A equals N over T. So let's sub in the number of decays 1,800 and divide that by 3, but we need to convert the minutes into seconds because remember time is measured in seconds. So 3 times 60 there is 180. So 1,800 over 180 gives me 10 becquerels. So that means my answer is A. Question 23 says the crew on an aircraft during a transatlantic flight are exposed to cosmic radiation at an equivalent dose rate of 5 microsieverts per hour. The crew completes 6 transatlantic flights each month. The average duration of a flight is 8 hours. The equivalent dose received by the crew due to cosmic radiation during transatlantic flights in 1 year is. Well, notice how we're given lots of data here. We're given the equivalent dose rate and we want to find the equivalent dose in 1 year. So I'm going to start by calculating the equivalent dose for one flight. So per flight we can say h dot equals h over t, but we want to find what h is because that's the equivalent dose. So let's rearrange for h to get h equals h dot times t, and we can sub in our 5.0 microsieverts per hour, and we can see that our answers are all in microsieverts, so I'm going to leave the answer in micro here and just remember to put it in at the end. So I've got 5.0 times the 8 hours for the flight, which gives me 40 microsieverts. So for one flight, the crew receives 40 microsieverts. But because there's 6 flights each month, we can think about the equivalent dose received per month. So because there's 6 flights in a month, we can do 6 times the 40 is equal to 240 microsieverts. And because there's 12 months in 1 year, we can now calculate the equivalent dose per year and say it's going to be 240 times 12, which equals 2,880 microsieverts, which gives the answer E. Question 24 says a radioactive tracer is injected into a patient to enable doctors to check the function of a patient's kidneys. Radiation from the tracer is monitored outside the patient's body by a detector. Which row in the table shows the most suitable type of radiation emitted and the half-life for the tracer? Well, if you've seen my theory video on uses of radiation, you'll remember that we talked about radioactive tracers and how we're always going to use gamma radiation for a radioactive tracer. And that's because they are detected outside a patient's body, so the gamma rays have to pass through a patient's body, and they're the only type of radiation that can do that. Alpha and beta are going to be absorbed inside the body, so would be useless as a radioactive tracer. So it's going to be either D or E here as our answer. And to think about the half-life for the tracer, if you think about a patient being administered with a radioactive tracer when they go into hospital in the morning, you would like to think that the radiation inside their body when they leave the hospital later that day is going to be at a safe enough level for them to go about their everyday lives. So having a half-life, which remember is the time taken for the activity of a source to decrease to half its original value of 6 years, is going to be way too long for the radiation to be at a safe level for the patient. Whereas a half-life of 6 hours is pretty reasonable because it means that somebody could go into hospital in the morning, be injected with the tracer, and then when they leave hospital later that day, the radiation inside their body is going to be at a safe level. So we're looking at 6 hours and gamma radiation, which gives the answer D. Lastly, question 25 says the activity of a radioactive source is 56 megabecquerels. The activity of the source 40 hours later is 3.5 megabecquerels. The half-life of this source is. Notice how we're given a time and an initial and final activity, and we're asked to calculate half-life. So we're going to use the numerical method for calculating half-life, where we use the arrows. So let's write down the initial activity, 56 megabecquerels, and let's half this until we get to 3.5 megabecquerels. So halving this once gives us 28 megabecquerels, halving again gives 14 megabecquerels, halving that again gives 7 megabecquerels, and once more it gives 3.5 megabecquerels, and we're going to stop there because that's our final activity. And because we've halved it 4 times with 4 arrows, that suggests 4 half-lives. So we can say 4 half-lives equals 40 hours, and to get 1 half-life we just divide both sides by 4. To get 1 half-life equals 40 over 4 equals 10 hours. So that gives me the answer B. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.